A different implementation of the consumer. It's very much the same. What's that? I don't know what verbose is. Oh yeah. I've introduced the Boolean verbose so that I can turn output on and off, and I've added that to the constructor. So how do you kill a consumer of the buffer? How do you know when the producers have added the last element to the buffer? I can tell a little story. I was once at an airport. I don't remember which airport it was. I was waiting for my suitcase. And when you're waiting for your suitcase, the suitcases come in batches, so you never know how long to wait. Because although there are no more suitcases on the conveyor belt, another batch might come. So I was waiting and waiting, and finally I saw a big red suitcase come on the conveyor belt. It was a big sign said, "Last suitcase, do not remove." And I thought that was pretty nifty that the baggage handling people at this airport had implemented what's called or known as the poison pill protocol. Instead of putting a poison pill onto the conveyor belt, they put a big suitcase. And that is how, in this implementation, we're going to kill the consumers by putting a poison pill onto the buffer. When the consumers see that pill, they will stop and exit. And so I have this static final in poison pill, giving it a value that is never added to the buffer otherwise, because all the values that are added to the buffer are between 0 and 9 inclusive. So it has to be distinguishable from the elements that are normally added to the buffer. And then I put the try block inside the while loop this time. And instead of saying while true do, I say while running. And then before removing something from the buffer, the consumer first takes a peek. If it's a poison pill, if it's not the poison pill, it can remove it. If it is the poison pill, it has to leave it on the buffer so that other consumers can see it. Because if it removes it, then other consumers will never see the poison pill. Notice here again that I've synchronized. Although all the synchronization happens in the buffer, there's more synchronization to do here because we have additional invariants that we want to have. We want to ensure that the poison pill is never removed from the buffer. And so if we don't synchronize, it can happen that one consumer checks that the first item on the buffer is not the poison pill. Meantime, somebody removes that first item, and now the next item is the poison pill, and the first consumer removes that the poison pill. And when we synchronize, we have to synchronize on something that all the consumers share, and that object is the buffer itself. So here we have synchronized on the buffer. Another important thing is that we don't hug the lock. So consumers will process the item down here, and if I move that statement up into where inside that synchronized block, then that will hog that lock until the item is processed, and the processing take quite a long time, and you would stop all the other threads from being able to access the buffer. So that's another thing one has to pay attention to.
But wouldn't it make sense to turn the synchronized buffer around in the peak, so that the peak is non-blocking, right?
Oh yeah.
In this case, so you could actually, it would be more performant. Otherwise, you're blocking it and then you're peaking, and only one thread can peak at a time.
That's a very good question. If I'm in control of the buffer implementation, I can do exactly what you said. I could have like something that remove if not equal to, and that's something that's been done with a lot of new classes that were added in Java 1.5. There's, for instance, there's a concurrent hash map, which has additional methods where you can say replace if not present or something like that. And but let's assume that this buffer belongs to somebody else. I don't have access to the source code, or maybe I have access to the source code, but I don't want to start mucking around with it. I'm the client of that software, and I have to take care of my own synchronization. I don't think it's that bad performance-wise, because locks are so-called reentrant. That means that once a thread has acquired a lock, it doesn't need to reacquire it. You just bump up the counter and then bump it down again when you exit a synchronized block. So in this case, it acquires the lock, the buffer, and then when it peaks, it already has acquired the lock. So it's not that bad in this case, but it's a good point. So that's how the consumer works. Now the producer there are a few changes here. I have put the try catch block inside the while loop. The consumer, there was no way I could kill the consumer other than by putting the poison pill onto the buffer. The producer, I might want to kill in different ways. So I have a stop method that what it does, it changes the value of this running boolean that it checks in every iteration. And that would be the graceful way of killing a producer, because it ensures that every item that the producer produces actually gets added to the buffer. However, to some software, the producer might just be a runnable, and that other software doesn't know other than the methods that you have in runnable, and it will maybe try to kill the producer by interrupting it. So therefore, the user should regularly check the interrupt status. So that's what we have here. And that means you can interrupt the producer although it's not in the waiting state. If by any chance it is in the waiting state when it's interrupted, when an interrupt exception is thrown, the interrupt status is cleared. So you have to re-establish the interrupt status. That's not only important so that you know how to exit the while loop here, but if the producer is running on some worker thread and somebody wants to actually interrupt the worker thread and not the producer itself, it has to be able to pass that interrupt status up the stack. So that's another thing that you always have to take care of, always re-establishing the interrupt status. So there's the stop method. So if we run this, same as before. It runs for about 1 second, and then the main thread here initiates shutdown. We see that producer 0 almost immediately is done. Producer 1 has this one item that has produced that it hasn't placed on the buffer yet, so it places it on the buffer and then exits gracefully. And then the main thread adds the poison pill. And the consumers continue running until that poison pill is in the very beginning of the buffer, and then all the consumers die very quickly. At the very end, the main thread removes the poison pill, and the buffer is empty. So now back to my presentation. So I think I went over the use of wait, notify all. Thread sleep we saw an example of. Concurrent thread, I think I didn't point it out, but that is a method that returns the thread that is currently invoking the methods. I didn't show this T. If T is a thread, you can wait for that T to reach its terminal state. And get name, I used that, you saw that. I even changed the name. Then volatile, I explained very briefly. I will get back to volatile. Somebody said that volatile is kind of confusing. I did point out that buffer is thread safe. And then in the more updated version, it's important to note it's the same buffer implementation. Nothing has changed with the buffer implementation. It's only how you use the buffer that changed. We use the poison pill protocol. I showed an example of what's called client-side synchronization in the consumer. The consumer had to synchronize on the buffer in order to peek and then remove. Every time you do something like check, then act, you should make sure that that is in an atomic unit, and you do that by synchronization. I showed that you had to check the interrupt status regularly, because otherwise the thread can go on for quite a while before it gets interrupted. I pointed out the importance of re-establishing the interrupt status if an exception is thrown, because the exception clears the interrupt status. And I showed the two different ways of creating a thread. One is by extending thread, the other one is to pass and runnable to the constructor of the thread. I mentioned this very briefly, but here's a more rigorous summary of the different thread states. There are six thread states. New, when a thread is created or instantiated after calling the constructor of a thread, it immediately enters the new state. And then when you call the start method on the thread, it enters the runnable state. Contrary to what some textbooks say, there's no running versus runnable state. There's just one state, runnable. Then there's the block waiting and time waiting states, and when the thread returns from those states, then it becomes runnable again. Block means that the thread is waiting for to acquire a lock. And a lock is, when I explain this to kids that I'm teaching, I say it's like a talking stick. Many of my students have been in Indian guys. I don't know if any one of you have done that with your son or did it as a kid, but in Indian guys, you have sometimes the tribal council, and everybody sits in a ring, and only the person who has the talking stick can talk. And so an intrinsic lock is just like a talking stick. Only the thread that holds the talking stick or the intrinsic lock can access a synchronized block or a synchronized method. So if somebody in that ring and in the tribal council raises his hand and says, I want to speak, but somebody else is holding the talking stick, that person would be in the blocked state. Now, if that person doesn't want to talk and is just listening to the birds and something else, then that person would be in the runnable state. Now, assuming that the guy gets to his talking stick and says, oh, I forgot what I wanted to say. Well, then he has to give up the talking stick and then exit the tribal council ring. And then if somebody else gets a talking stick and is kind enough to say, notify all, everybody who has had to exit the council can now return to the places inside the council ring and they become runnable. Terminated is when the thread run method returns, or after throwing an unquote runtime exception. And once a thread has reached its terminate state, it's terminated. Can't exit that state. So this example, we learned some lessons. Just summarizing them here. Always call wait inside a while loop and recheck the condition after being notified. Use notify all rather than notify. There are two methods, notify and notify all, and I've seen a lot of forum posts that said, why can't I just call notify? Why do I have to call notify all? And the figure here shows an example why notify will not work. So at first, this is how I study threads. The rectangles corresponds to threads, the ovals corresponds to an object, and thread calls methods on objects. And then when the method returns, I show that by an arrow that goes from the object back to the thread, and I draw a vertical line to connect the arrow in one direction with the corresponding arrow in the other direction. So assume the thread C1 first calls remove on the buffer. The buffer is empty, so C1 enters the waiting state, and that's shown by a red color there. Then C2 tries to remove something, same thing happens. Then P, which is a producer, adds an element E1. That works fine, the buffer is empty, there's capacity, it returns immediately. When it returns, just before returning, it calls notify. When you call notify, not all the threads that are in the waiting states wake up, only one of them, one at random. Now let's assume that C2 that is woken up. So C2 becomes runnable after the add method up here returns. Now the two runnable threads. Now assume that P acquires the lock again. So P goes first and tries to add an element E2, but the buffer capacity is 1 here, so that method blocks. The P goes into the waiting state and releases the lock. Now C2 is the only runnable thread, acquires the lock and completes the remove method, and just before removing it calls notify, which is going to wake one of the two threads that are in the waiting states. Let's assume it's the C1 that gets woken up. Now C1 has to complete the remove method, and what it does when it wakes up, it rechecks the condition, which means calling is empty on the buffer, which returns true. So C1 just goes immediately back to the waiting state. At that point, In time, C2 is the only runnable state, runnable thread. It tries to move again, but the buffer is empty. So it enters the waiting state. And at that point in time, all threads are in the waiting state, so there's no more progress. And we need a fourth thread to interrupt them in order to make progress. So one way around this is...
One question.
Yeah.
So when you have multi-CPUs, how the single thread or multi-thread can be with that?
I didn't understand the question.
Okay, so you have, like, if you have one CPU, certainly one time you can run one thread.
Yes.
But you have multi-CPUs.
Yeah.
When you notify all.
Yeah.
Where the number of CPUs threads will start running, or still only one?
All of them will exit the waiting state and go into the runnable state. Okay?
Right.
But in order to resume computation, execution, they have to acquire the lock, and only one of them can acquire the lock. So that's what is really confusing. Why wake up all of them when only one of them can acquire the lock? And it's random which one acquires the lock. But this example just showed it wouldn't work if you just call notify. It's pretty subtle. It's, so the lesson learned is always call notify all. Sometimes it's wasteful. Another option is to say, instead of calling wait, you can call timed wait. You can pass a timeout. And that would be a way to get out of this impasse that I've shown in this figure. And then you can use notify.
So, for example, you have 1,000 threads running, and you have 2 CPUs. So, every particular time, there are only 2 threads are running, right?
No, it's actually, running is not a state. But you can say, yes, actually performing some progress. There can be at most, actually only one, because only one can have acquired the lock, and there's only one lock. So even if you have 2 CPUs, only one can run.
Okay, thanks.
Is there an instance where you would want to use notify?
I think if, I think if you have hundreds of threads, I mean, this is a very peculiar, it's you know, random, you're very unlucky that this would happen. So it's kind of wasteful to wake up all the threads and then only one gets to run. And then maybe that thread just goes straight back to the waiting state, and another one tries and goes back to the waiting state until you actually, a producer gets the lock, and then it makes some progress. So if you have many threads, use notify, but then put a time limit on the wait so that you can get out of this situation.
Is it dependent on the thread pool? Also, if you use a thread pool, depending on the strategy that's used and how big it kind of reactivated?
If you use thread pools and you use the Java classes, library classes that exist, you will neither call wait or notify or notify all. It's all going to be implemented for you. So you're not going to worry about this.
Wouldn't you do it usually?
No, I don't know exactly how these things are implemented, but I'm going to talk a little bit about those things now. So volatile, in order to understand the meaning of volatile, you have to understand the Java memory model. And the Java memory model says that potentially every thread could run on its own CPU. And CPUs have local cache. If you update a variable, that update might only be done in the cache. You have to tell the compiler that it has to not only get the value that is stored in shared memory, bring it into the cache, update the value, and write it back onto the shared memory. And that is what synchronized block does. When you enter synchronized block, it tells the compiler that the thread has to go out and reach into the shared memory, get the value from there. And when it exits the synchronized block, it has to write it back into the shared memory. Now, if you have a primitive int, even a double, updating a double is not atomic necessarily, a 64-bit variable. Long is not atomic, but if you declare it as a volatile, there are two things that happens. The update becomes atomic, and you also telling the compiler that it has to go and get the value from the shared memory. So it guarantees visibility of an update of a volatile variable. So I had these Boolean empty and full, and one thread could change the value. But because I had declared those Booleans as volatile, I was sure that the updates became visible. References can also be declared volatile, but it's only the reference, not the object that the reference is referencing that becomes visible. This is taken from this. You can find this synchronization and Java memory model on the web.
So when you're doing the threading, is there specific things you look for that before you decide you need to use?
Is it something?
When you want to make, if you're writing a bunch of threaded code, what things do you look for to realize that you need to use all? I mean, I understand like what it's for and how it's working here, but sometimes it's hard to see those things before you have an issue.
Okay, so well, maybe that's something that I'm going to talk about right now. So you have to somehow, as I said in the very first slide, you have to be concurrency aware. You have to know which of your objects might be accessed by multiple threads. If you know that an object might be accessed by multiple threads, you have to make it thread safe. Because you can't trust the threads themselves to take care of the thread safety. Not every object needs to be thread safe. And this is what this slide here talks about. To avoid synchronization, and that's something you would do if possible, because there's a lot of overhead with synchronization. Use immutable objects. String is immutable. You can pass it around. You don't never need to synchronize anything on it. Functional programming language have a lot of immutable data structures. Lists, they have immutable lists. People think that that's a very waste of time because you have to copy the list, but actually it's not, because they're implemented very cleverly. Some of the Java classes that are introduced for concurrency purposes, for instance, a copy on write array list in Java, which copies the underlying array every time it's modified. And so any thread that accesses it will only see the array at that moment in time. And that array will not be modified by any other thread because it's going to be a copy of that array that is going to be modified. So that avoids synchronization. The other way is to confine an object. And there are two types of confinement. The one is thread confinement. That means only one thread can reach that object. So in the figure here, O3 is confined to the thread number 2. By the way, every thread corresponds to a stack. So a stack and a thread is kind of the same thing. Actually 2 stacks, because it's also the native stack, but the Java stack itself, the one that you see when you do a print stack trace. And I like to draw them going upwards, but down is what people call up. So because things get put on top, not filled in from the bottom. But that's the convention that we have to live with. So O3 here is confined to one thread. And there are ways to pass an object from one thread to another and maintain that thread confinement. Only one thread can access an object. The other thing is what's called instance confinement. So O2 can only be accessed through O1. So O1 can do the thread safety and make sure that only one thread can get to A2. So every thread has to get to O2 through O1, and that's some strategies that are often used. And I'm showing some of the Java classes that allow you to pass an object from one thread to another, and how you can confine objects to instances. Otherwise, you just have to be prepared. You have to look at, are there multiple threads that may access your object, and you have to make it thread safe.
So I've seen it used in, like, for example, the old style of creating singletons.
In where?
Creating a singleton object.
I didn't hear.
Creating a singleton.
Oh yeah.
And it's during the constructor phase, I guess.
Oh yeah, there's this famous double check blocking or something like that. Or no, yeah.
Double check.
Double check locking. And that's often referred to as an anti-pattern because it's broken.
Well, they fixed it in 1.5.
They fix it, but you have to copy that code exactly as the way they fix it, because it's impossible to derive that code yourself. I mean,
So the fix was adding volatile.
Yes. I've looked at that code. I haven't tried to understand it. If I'm ever going to use it, I will just go and copy it as written, put it into my code.
Unless you're at a job interview.
If I'm in a job interview, well, there's another. I read recently in Java 8 how to do that. I thought it was a better method for doing the same thing.
You can create an enum.
An enum is one way to do it.
But
you create
yeah.
static and then it's instantiated during time, instantiate the object, so, and then you can read from it. You don't need to
If you don't need to do lazy instantiation, you can actually, when you instantiate the object, you create the static object.
Yeah, there's a few ways to do it, but I noticed that was my first time running across needing to really understand it. Well, I'm still kind of getting confused about it. I have to really think about it because it's threaded.
Yeah. Another way is to using thunking. Instead of having that one instance, you have a function that returns that instance, and you can, at the beginning, you can have that function be a synchronous function, so that the first time you access it, then you replace that function with, once that singleton is instantiated, you replace that function with a non-synchronous function, so that you don't go through the synchronization every time after that. It's something I read fairly recently, and you had that Indian guy that I was talking about, Java 8 in spring, and I won his book in the lottery here, so get a lottery ticket. It's a good book. There's so many different practices, and there are, books about this. One that struck me as pretty useful was, sometimes you have to acquire multiple locks. Let's say you're going to transfer some money from one account to another account. You have to first acquire the lock of the account that you're transferring money from, and then you acquire the lock of the account that you're transferring money to. Now you have to acquire two locks before you can do the transfer. Now if another thread is doing the transfer in the other direction, it might acquire the lock of the first account. One thread might acquire the lock of the first account, the other thread acquires the lock of the second account, and both are waiting for the other lock. And that's a deadlock situation, and there's no way, absolutely no way to get out of that situation once it occurs. There's no interrupt, you just have to reboot your system, or you have to do a system exit and restart or something like that. transaction engines and databases, they have sinks that go around and resolve deadlocks like that, but in Java there's no such thing. So it's very important to avoid this. And one strategy here is to always acquire every lock in the same order. So you can use, for instance, the account number to decide which lock you acquire first. Every account has a unique account number. So the account that has the lowest number, you acquire that lock first. And you avoid these circular deadlock situations. They can be very tricky to discover. Using the library classes can be a way of avoiding them because you can avoid these situations. And there are some design patterns and frameworks that are built around them. Concurrency libraries, java.util.concurrent, and it has some sub-packages in there. Contains lots and lots of interfaces and classes. And then in Java 8 there's also Java util stream. Most of these classes in Java util concurrent were introduced in Java 1.5. Fork join, and that fork join framework was introduced in Java 1.7.
What happened to the atomic framework? It's one of these things that I used in the past, and that seems to get around blocks in general because you keep on reading the same value until it changes.
I didn't hear. I'm sorry.
The atomic framework that you had in there, is it still around? Is it still used?
I don't know. I didn't know that it was not used.
Because most examples that you find in books are always using synchronization blocks, whereas with atomics you don't synchronize, right?
No, you can have, for instance, have an atomic integer, and you can update it without having to do any synchronization.
Wouldn't this be a way around the synchronization blocks that you created before? Because you can have multiple threads reading at the same time. With atomics, you took the other approach. You're looking positive at the result. You always think that you can read it, that only if something goes wrong, you disappear threads back. Yeah. Whereas with a lock, you're always saying, okay, I'm acquiring the lock and nobody else can do anything. With atomics, it was switched around, right?
Yeah,
always allow everyone to read.
I haven't really looked into that. I don't know exactly how the atomics is implemented, but I've seen a lot of books referring to atomic and code samples. So it seems that it's. I don't know if it's more optimal to use atomics. I have to read more about it. I really don't know. So one of my favorite classes is, or interfaces, is blocking queue. The ring buffer that I showed is kind of a lightweight blocking queue implementation. It has several implementations: array blocking queue, linked list blocking queue, and so on. It has this very special implementation called synchronous queue, which is a queue of size 0, which allows two threads to have what's called a rendezvous. One thread executes to a certain point where it does a put, and there it blocks, until another thread does a take, and then they are at this point in their code, both of them at the same time, and then they do an exchange and then they continue. And if the take occurs before the put, then the same thing happens. There has to be a handshake there at that same point in time. Blocking queues have several methods. I mentioned earlier that you could throw an exception, or you could return a special value. So add throws an exception, offer returns immediately or after timeout, and it has a boolean to indicate whether something was added to the queue or not, and then put blocks. And then for remove, it's the same thing. Remove throws an exception if the buffer is empty or the queue is empty. Poll returns null if it's not able to remove anything. Null. I'm sure that if this was implemented after Java 8, it wouldn't return null, it would return an optional. But this would happen before then, and then take locks just like before. It's a very important ingredient in the producer-consumer design pattern, which is used everywhere, and the consumer-producer, or the producer-consumer pattern is an important ingredient in other more complex patterns. You refer to it allows for separation of invocation and execution. You can say, I want this done, without having to say when it's done or by whom it's going to be done. And then you just put it on the blocking queue, and then some other thread will eventually execute a task. So you can put tasks onto the blocking queue. I was talking about thread confinement. It's a way you can pass one object to another, from one thread to another thread. You can build pipelines. So you have, for instance, a tokenizer, puts it on the blocking queue, parser takes it off the blocking queue and processes it. You can have a web crawler, finds a page, puts it on the blocking queue, and some other thread does the indexing. It can make code very nice and simple. I like to compare it to, let's say, the workshops that made cars in the early 20th century, where there were a lot of guys around the car and trying to build it up from scratch, putting parts together. And it took a very long time to build a car, and the cars were very, very costly. And at one point, Henry Ford came along and says, no, we're going to build an assembly line. And the assembly line is these pipelines that you can build with blocking queues. They can also be used to manage workload. If you use the offer method to put a task on a blocking queue, offer will return if there's no space. So that gives you a sort of graceful degradation. Blocking deck is another interface. It's a deck means double-ended queue, and there's one implementation. It's sometimes used for work stealing. Think about the lines at the grocery store. Your line is progressing very slowly. The cashier is the worker's thread, and it's taking care of all the customers. So what do, you put people at the end of the queue, they move to another queue. And the other cashier is now stealing work from the first cashier. So that's kind of work stealing. And work decks are used for that. How much time do I have left now? I'm trying to rush here a little bit.
It's a little bit after 9.
Okay, I'll rush. All these are very well documented in the Java API. I'm just going very quickly through them here. Counting down latch. If you want something to happen after certain events have happened, you want to then unleash a thread. You can use a countdown latch. It acts as a kind of gate. If I want to test my consumers and producers, I want to unleash them all at the same time. I don't want to first start the producers or first start the consumers. I can use a countdown latch. If I have 10 consumers and 10 producers, I count down to 20 and then all start at the same time. There's example code and how to use it in the Java API. Cyclic barrier. I mentioned how the synchronous queue can use to have a rendezvous two threads. Cyclic barriers can be used to have a rendezvous across multiple threads. The latch, once it's used, it's a one-time thing. The cyclic barrier can be used multiple times. So an example here, you're running a traffic simulation, and every vehicle runs in its own thread. And you want to make sure that simulated time for all the vehicles is the same at the same time. You can't have one having simulated 10 minutes and the other one simulated 5 minutes, because the way that the vehicles should behave is dependent on the vehicles in the traffic. you can't drive through vehicles, so you have to drive around them or stop in time. And so you can have a cyclic barrier that says you take one simulation step and then you have a cyclic barrier. All the threads, when they have performed that simulation step, when they're finished doing it, they do the next step and so on. And so that's how the cyclic barrier can be used. Semaphore, it's a counting semaphore. It distributes permits, and so you can have an activity has to acquire a permit in order to do something, and then when it's done it can release the permit. So it's not actually a physical permit, it's just a number, and the semaphore keeps track of the number of acquired permits and the number of release permits. So it can be used to impose bounds. So if you have an implementation of hash set, for instance, you can make it into a bounded hash set by having a semaphore, and you have to acquire, and then that provides a certain number of permits. When that number of permits has been exhausted, then your hash set is full. Again, the Java API provides example code. Futures is really neat. I can try to illustrate this with a story. Peter is a software developer, lives in San Francisco. There's a bakery, French bakery, just 2 blocks from where he lives. Every morning he does the same routine. He gets up, goes to the bakery, gets a baguette, goes back, has breakfast, and goes off to work. Comes back from work at 6 o'clock in the evening. Same schedule. He's partly OCD, never changes. He's just like a program. And then one day he wants to invite his girlfriend over to tea. So he goes to the baker to buy his baguette, and then he asks the baker, do you make cakes? And the baker says, yes, I do. Come back at 3, it will be ready then. And Peter gets a panic attack and says, he starts tripping back and forth. He doesn't know what to do because it's going to mess up his whole schedule. So the baker says, don't worry, and he goes back in the back of the store and comes out with a box about this size and gives it to Peter. And he says, go home, put it in the fridge, but don't open the box until 3 o'clock. And so Peter goes about in his normal day, goes to work, comes back at 5:30, takes the cake out of the fridge, opens the box, or the box out of the fridge, opens it, there's a cake inside there, magic, and everything works. And that's how a future works. It's something that you can order that is going to be ready, and sometimes in the future you don't need to worry about waiting for it, or it runs in its own, it can run it in its own thread, and so it's very convenient. You don't need to change code in order to get something done. A future task is an implementation of a future. It wraps around a callable. A callable is like a runnable, but it returns a value. And so that's the value that is returned by the callable. You can also pass a runnable to a future and a particular value to return when that runnable has completed. It has method to cancel, to query where it is done, and to get the value that is once it has completed. If you call get before the future has completed, that get will just block. So important not to call. Don't open the cake box until 3 o'clock, kind of thing. And then fork join task was added in 1.7, very similar to future. Java 8 uses fork join task to implement stream parallel. And if I was ever going to use fork join task, I would rather use stream, not parallel. They're used for things that can run in parallel, independent of each other. For instance, doing large matrix multiplications. Every element in the product can be computed independent of everything else. So you can have true parallelization, no need to synchronize or anything like that. and it's purely functional. Image processing, you can use a future task, and it's really used to get the most out of multiple cores. So executor framework allows you to invoke new threads in a new fashion. To the left here, it's like I showed in the example. Today you would rather use an executor. So on the right is how you would do the same thing with an executor. Executors is a factory class, and it has multiple methods here. Create a fixed size thread pool, and then you have a runnable, and you just tell the executor execute this, and it will allocate a thread in the thread pool and run the task for you. And that's a much better way to do it, because you have better resource control, how many threads you're running, and you don't have the overhead of creating and new threads, which is has a certain overhead with to create it. They're large objects, and so you want to avoid that. The executor interface itself has only one method, execute. So you can make your own executor. For instance, the first line there, new thread r.start. That's the conventional way of starting it. If you want to really stick to that, you can do that, but that's not really the purpose. It just shows that when you're using executors, you're kind of uncoupling the actually runnable from how it's being executed. You're not, unlike, when I created a consumer by extending the thread class, I was kind of locked into that way of executing the consumer. There's a bunch of factory methods. Fixed pool, cache thread pool. It's like if you need an extra worker thread, it will create one, but then it puts it into the pool and you have it there for later use. Single thread executor, if you want just a single thread, it's like a fixed thread pool of size 1. A scheduled thread pool can be used to run tasks at regular intervals of time. So it's instead of using java.util.timer where you execute the task at certain intervals, it's much better to use the new scheduled thread pool for that purpose. Executor is an extension of executor. It has several methods to take care of the lifecycle. You can shut down an executor service, and you can monitor when it's terminated and so on. And the Java APIs shows example code. And that brings me to the last slide. I was going to have a bibliography slide, but I didn't have time to write it. I will put that bibliography before I send the slides to you, and I don't know where you're going to put it.
The slide?
The slides, yeah.
On the website.
On the website?
Yes.
Okay, so I'll just send an email with the slides. I'll do a few updates. It's a bibliography. It's a lot of interesting reading. You can find lots on the web online, and there are a few good books. I used Doug Lea's book on concurrent programming in Java. I used a book that was written by, what is his first name? Goetz. Brian Goetz, yeah, and a bunch of other authors. I found that book very easy to read, very well written, better than Doug Lea's, because that's a little bit hard to follow. It's a good book, but it's hard to read. I used the book from Venkat, the Indian guy that talked about Java 8. I found Joshua Bloch's Effective Java has a section on how to do concurrent programming. A few items on concurrent programming. Much of the stuff in my first example code was taken from there, or the general rules like putting weight inside a while block and so on, using notify all rather than notify and these things. So there's a lot of stuff there, and I'm fascinated by this. I like it, and it's cool. It's very difficult to test because deadlocks occur very may occur very frequently and you never notice them, and so you have to do these soap tests with hundreds and hundreds of threads and run for a very long time in order to discover bugs. So that's the end of my talk. I don't know if there are any questions. Sorry for going over time.
Okay.
Just from a strategy, which of these approaches would be used yourself from a performance perspective, from a stability perspective? It looks like there are trade-offs between different ways of how to synchronize and how to deal with threads.
I would definitely use like an executor or an executor servers to do this. Now, you can use that in combination with, for instance, a barrier, cyclic barrier, and a latch. And these have special purposes in order to synchronize the threads, but having the threads running inside an executor or inside a thread pool, I think that's very common. There are ways to avoid creating too many threads. I didn't talk about it, but this is reactor pattern, which replaces concurrency by doing a more event-based processing. It's, for instance, when you are doing GUI implementation, instead of having a thread that listens to one specific event and it's blocked most of the time until somebody presses a button, you just take all these events and then you have a demultiplexer that finds out what's the source and who is listening to this, and then dispatches this to the different listeners. That's the reactor pattern, how it's used in GUI. It's an important pattern. It's also used, for instance, for accessing a server. Java.nio, which is a new I/O, has a whole framework in there for doing non-blocking I/O using that reactor pattern. So avoid threads if you can, but just be aware about they are there. Replacing threads with event is sometimes more messy because you have to process every little event individually, whereas if you process them in a thread, you have the whole stack to help you with keeping track of the state and a context for processing multiple events.
How would you see it compared to something like the ring buffer that's used in Node.js and in the Vertex?
I'm sorry, you have to speak up a little.
Ring buffers.
Yeah.
That are used in Node.js, like the approach where you have only a one-threaded model, and you basically get rid of the switching overhead. By doing that, you can actually do more things with one thread.
What's the ring buffer?
How do you compare these different approaches?
I don't know. I haven't read it. I haven't experimented.
Node.js uses a single threaded environment, the ring buffer. It just takes it and start processing it. It's event-driven. When it's done, it's going to notify.
And Nginx, like all
and
these
Vertex does the same thing.
The same thing, and we're more performance, looks like. Right?
Yeah.
We seem to have better results.
Yeah.
With these approaches.
Yeah, I mean, context switching has a certain overhead. You want to avoid that. So event. I gave a talk like a few years ago about replacing event with threads, and I remember you asking a question, how did it perform? And I didn't know what the answer was, but because I thought that the user interaction was the bottleneck here. But then I went home and I simulated this, and what I did was, if you're doing event, you have to have a state machine to know how to connect the different events together. And doing a state machine event processing was much faster. It wasn't beyond comparison. So, but it adds more complexity. The code becomes more complex. So if you do it when you have time-critical, performance-critical code, you have more complex code, but you get better performance.
Okay, thank you very much, Erik.